Hi friends, in our last video we have completed Euler-Phi function and some theorems or properties on that Euler-Phi function. Next we'll continue the same. The next theorem is prove that phi of n is equal to n into 1 minus 1 upon p1 into 1 minus 1 upon p2 so on up to 1 minus 1 upon pr, where p1, p2, p3 so on up to pr are distinct prime factors of n. By using fundamental theorem of arithmetic, we know that any number n can be expressed as a different in the prime factorization in a unique way. Each that prime numbers are distinct. If you express in a standard form, then you're getting each prime numbers are distinct here. So like that, since we have this p1 proof here, p1, p2, p3 so on up to pr are distinct prime factors of n. Therefore, we can write n is equal to p1 raised to k1, p2 raised to k2, so on up to pr raised to kr by using that fundamental theorem of arithmetic. Next, we have to calculate phi of n. As each of these prime numbers are distinct, just by using the previous theorem, whatever you have taken, that phi of ab, if a and b are relatively prime to each other, then phi of ab is equal to phi of a into phi of b. Then we can extend for n number of terms also. By using that theorem, we can write here phi of n is equal to phi of p1 raised to k1, phi of p2 raised to k2, phi of pr raised to kr. Then that is what? Phi of p1 raised to k1. Already we have seen that if p is a prime number, then p raised to n, or phi of that p raised to n we can write as a p raised to n into 1 minus 1 upon p1. So by using that theorem, we can write p1 raised to k1. Phi of p1 raised to k1 is equal to p1 raised to k1 into 1 minus 1 upon p1. Phi of p2 raised to k2 is equal to p2 raised to k2 into 1 minus 1 upon p2 and so on. Phi of pr raised to kr is equal to pr raised to kr into 1 minus 1 upon pr. That is what these terms are taken one side, p1 raised to k1, p2 raised to k2, pr raised to kr, and this bracket one side. Now this p1 raised to k1 into p2 raised to k2 into so on up to pr raised to kr is equal to n by using this equation, and n into these terms are as it is, that is the required n, phi of n equal to n into 1 minus 1 upon p1 into 1 minus 1 upon p2 and so on up to 1 minus 1 upon pr, where p1, p2, p3 so on are distinct prime factors of n. See, we'll see the example here. One example I have solved here, that is find the number of positive integers less than or equal to 3600 that co-prime to 3600. See here, they are not asked directly as a phi of n. That they are asked by using the definition. We know by using definition, number of positive integers less than or equal to that n and co-prime or relatively prime to n is nothing but phi of n. So in this also we need to calculate phi of n itself. So therefore we will take an n equal to 3600. That 3600 is expressed in standard form. Like this, go on dividing and express in standard form. We're getting 3600 is equal to 2 raised to 4, 3 square into 5 square. So therefore, phi of n is equal to phi of 3600, that is phi of 2 raised to 4, 3 square, 5 square. Observe here, 2, 3 and 5, these are the distinct prime factors of 3600. Then just by using this formula, phi of n equal to this one. So n is as it is, 3600, 1 minus 1 upon p1, p1 is 2, into 1 minus 1 upon p2, p2 is 3, into 1 minus 1 upon p3, that is p3 is 5 here. So simplifying this, we are getting phi of 3600 is equal to 960. Yes, in the similar way, you have to try these examples. That is phi of 768, you need to calculate, we are getting answer as a 256. Similarly, 2205, for this we are getting phi of 2205 is equal to 1008. You try these examples. Next, some theorems, again examples we'll consider from Fermat's theorem. Prove that a raised to 12 minus 1 is divisible by 7 for all a such that a and 7 are relatively prime to each other. GCD of a and 7 equal to 1 means a and 7 are relatively prime to each other. See, since a and 7 are relatively prime to each other, by Fermat's theorem, we have a raised to 6 is congruent to 1 mod 7. We know that whenever a and n are relatively prime to each other, then a raised to n minus 1 is congruent to 1 mod n, or m if it is given, then a raised to m minus 1 is congruent to a mod m. Then, so here by using that Fermat's theorem, what you're getting, n minus 1 is 6. 7 minus 1 is 6. 7 a raised to 6 is congruent to 1 minus 1 mod 7. So squaring on both sides, we need here a raised to 12. So I'll take square on both sides. A raised to 12 is congruent to 1 square mod 7. 1 square is 1 itself. So there, that you can take left side, or else a raised to 12 is congruent to 1 mod 7. That implies, according to definition, 7 divides a raised to 12 minus 1, or a raised to 12 minus 1 is divisible by 7. This is the first example. Next, the second one. Prove that a raised to 18 minus b raised to 18 is divisible by 133 if a and b are relatively prime to 133. Yes, if a and b are relatively prime to 133, then we need to prove that a raised to 18 minus b raised to 18 is divisible by 133. So again, I will use the Fermat's theorem itself. So, but see, first of all, what we have, 133 is equal to 7 into 19. 7 is a prime number, 19 is a prime number. So we can apply the Fermat's theorem here. As a is relatively prime to 113, it should be relatively prime to 13 also. Sorry, 7 also. Here it is not 13. A is relatively prime to 133. Therefore, it should be relatively prime to 7 also. Therefore, by using Fermat's theorem, as 7 is a prime number and a is relatively prime to 7, a raised to 6 is congruent to 1 mod 7. Taking cube root on both sides, we are getting a raised to 18 is congruent to 1 mod 7. That is equation 1. Similarly, see, since 7 is a prime number and b is congruent to 133, we have, b is relatively prime to 133. We have b is relatively prime to 7 also. Therefore, b raised to 6 is congruent to 1 mod 7. Again, taking cube on both sides, we are getting b raised to 18 is congruent to 1 mod 7. That is equation 2. Now from equation 1 and 2, we can write equation 1 is a raised to 18 is congruent to 1 mod 7. Equation 2 is b raised to 18 is congruent to 0 mod 7. Therefore, from 1 and 2, we are getting a raised to 18 minus b raised to 18 is congruent to 0 mod 7. Also, since 19 is a prime number and a and 133 are relatively prime, this implies a and 19 are also relatively prime. Therefore, by using Fermat's theorem, a raised to 18 is congruent to 1 mod 19. Similarly, b raised to 18 is congruent to 1 mod 19 because b is also relatively prime to 19 we are getting. Therefore, from equation 4 and 5, a raised to 18 minus b raised to 18 is congruent to 0 mod 19 because while subtracting these two equations, we are getting right side as a 0. Therefore, see, a raised to 18 minus b raised to 18 is congruent to 0 mod 7 and a raised to 18 minus b raised to 18 is congruent to 0 mod 19. Therefore, by combining equation 3 and 6, we are getting a raised to 18 minus b raised to 18 is congruent to 0 mod 7 into 19, that is 133. That is what we got here. A raised to 18 minus b raised to 18 is congruent to 0 mod 133, or 133 divides a raised to 18 minus b raised to 18, or a raised to 18 minus b raised to 18 is divisible by 133. Next, similar example, prove that 2 raised to 48 is congruent to 1 mod 105. Now we'll see 105 is equal to 3 into 5 into 7, where 3, 5, 7 are prime numbers, distinct prime numbers we have. Now, since 3 is prime and 2 and 3 are relatively prime to each other, we have, by using Fermat's theorem, directly we can write by using Fermat's theorem 2 square, because 3 is the prime number, 2 square is congruent to 1 mod 3. Then taking raising power 24 on both sides, so getting left side 2 raised to 48 is congruent to 1 mod 3. That is equation 1. Similarly, 5 is a prime number and 2 and 5 are relatively prime to each other. Therefore, by Fermat's theorem, 2 raised to 4 is congruent to 1 mod 5. Next, raising power 12 on both sides, we are getting 2 raised to 48 is congruent to 1 mod 5. That is equation 2. Similarly, 7 is a prime and 2 and 7 are relatively prime to each other. Therefore, 2 raised to 6 is congruent to 1 mod 7 by using Fermat's theorem it is. Then raising power 8 on both sides, we are getting 2 raised to 48 is congruent to 1 mod 7. Therefore, from 1, 2 and 3, we have 2 raised to 48 is congruent to 1 mod 5 into 7 into 3, that is 105. Therefore, 2 raised to 48 is congruent to 1 mod 105. Yes, this is about some theorems in Euler's theorem and examples on Fermat's theorem. Next concept is the Euler's theorem that will continue in next class.